So graphs of motion for projectiles. The first thing to know is a projectile is something that's acted upon only by the force due to gravity. The only force acting on it is its weight. We neglect air resistance. We neglect any other forces acting on it. So the simplest example of a projectile is this. This would be over here in pink. A ball thrown up in the air, or some object thrown up in the air, returning to its starting point. So we know that initially, when it's thrown up, it will slow down as it rises. Up here at the top, it will stop for a minute. Oops, I got the wrong thing here. Up here at the top, it'll stop for a minute. Its velocity will be 0. And then it will fall down back towards the center of the earth. And it will speed up as it does so. It will accelerate at a rate of g. And g is always downward towards the center of the earth. So let's look at this, the two parts of this trip, the trip up, the trip down, and then we'll combine them for the trip up and the trip down. For the trip up, I have decided that upward will be positive and downward will be negative. You could do the opposite if you want. I don't know why I would, but you could. So on the way up, it's got a positive velocity. That means its displacement will be positive. It will end up in a higher position than where it started. I'll start it out at 0, at a position of 0, but you could start it anywhere. There's no information given to you that says this has to start at 0, so we can start it wherever we want. But we'll say it starts at 0, and it accelerates at a constant rate of g, and it has a positive velocity. So positive velocity slowing down would look something like that. What would the velocity time graph look like? Positive velocity would mean it's above the horizontal axis. That's where the positive velocities are. Remember, a velocity of 0 would be right here at the horizontal axis. And slowing down would mean approaching 0, and that would be a straight line. It doesn't mean it would be a constant velocity. It just means the velocity would be changing at a constant rate. The rate at which velocity changes is acceleration. And the slope of a velocity time graph is acceleration. Here we see there's a constant negative slope. Therefore, there would be a constant negative acceleration. Hopefully, you would realize this anyway. The acceleration is g. It's downward, and I've called downward negative. And g is constant. At or near Earth's surface, it is 9.8 meters per second every second. On the trip down, it has a negative velocity. I've decided that downward's negative, so it's got a negative velocity, and it is speeding up on the trip down. Negative velocity speeding up would look something like that. Negative velocity in a velocity time graph means it would be graphed below the horizontal axis. Remember, it stops at an instant up here. Its velocity is 0 meters per second before it starts back down again. So we can start this at 0, and we can show it has a constant negative acceleration. The slope of a velocity time graph's acceleration. So there is the acceleration time graph for that. If I put both of these together, I have this initially moving at the positive velocity and slowing down, and then moving with a negative velocity and speeding up. And it would look like this. What would the velocity time graph look like? Well, it would look like a positive velocity slowing down. It would start somewhere here. It would hit 0. This is that instant right here, this point. We mark it. That's where velocity would equal 0. That would be the instant that it's at the top of its trajectory. And the slope of a velocity time graph is acceleration, so this would be a constant negative acceleration. So here we just have something that is launched upward. Here's a projectile that's moving in 2 dimensions, which means it's moving up and down along the vertical axis and also across along the horizontal or the x-axis. Just like in a graph, we would call the horizontal the x and the vertical the y. And I put an orange line down the middle for the trip up, and I called that portion of its motion part 1. And on the right side there, that part 2, that's the trip down. So what we're going to see is that this is no different. These graphs are going to be absolutely no different from just throwing a ball up in the air and catching it again, regardless of whether it's moving sideways or not. Remember, horizontal and vertical motion are completely independent of each other. So let's look at the position time graph for this first part of the graph that I marked number 1. It's going in a positive direction, and actually I didn't indicate that, but let me indicate that. We'll say that up is positive and downward's negative. So it has a positive velocity and it's slowing down. We'll say it starts at 0. We don't have to, but we will. Starts at 0, positive velocity slowing down. It would look something like that. Positive velocity slowing down. It would look something like that. And it does come to rest at the top, so I can have it touch the horizontal axis where velocity is 0. And acceleration time, this is a projectile. The acceleration is always downward, and it is 9.8 meters per second every second. It's a constant negative acceleration in this case because I call it downward negative. Acceleration is also the slope of a velocity time graph. We see here a constant negative slope, constant negative acceleration. Now let's look at part 2. Here we have this thing moving in a negative direction, right? It's going down, and I said down was negative. It's got a negative velocity, and we know here it's going to be speeding up. So we'll start it at some point above 0. We'll show it a negative velocity speeding up. It's getting steeper. With velocity time, at the top of its trajectory, its velocity was 0. So we will have it start at 0 and then have a negative velocity. It's moving downward in a negative direction, negative velocity. And the slope of the velocity time graph's acceleration, constant negative slope, constant negative acceleration. And again, the only thing accelerating it is the force due to gravity, or its weight, and that is straight downward. So that doesn't change. Acceleration's downward no matter how this thing is moving. Then if I put them together, I have something that is going in a positive direction and slowing down, stopping for an instant, and then moving in a negative direction and speeding up. Would look something like that. Positive direction slowing down, negative direction speeding up, it would look like that. And again, constant negative slope in a velocity time graph means a constant negative acceleration. That is what that would look like. Now what about the horizontal component of motion? When we do free fall problems, we know that the motion along the horizontal is constant. The only force acting on it is gravity. That force is acting downward. There is nothing at all acting along the horizontal. So that motion is constant. It's moving, but it's moving at a constant velocity along the horizontal. In this case, you can see here I did it in pink. I said that the positive direction was to the right. I could have said it was to the left. I just didn't. How do I represent a constant positive velocity in a position time graph? I'll start it at 0. I don't have to, but I will. That is a constant positive velocity. The slope of a position time graph is velocity. If it's a constant slope, it's a constant velocity. If it's a positive slope, it's a positive velocity. Along the horizontal, it just doesn't matter that this thing is also going up and down. It does not affect that horizontal aspect of its motion at all. So the slope of a position time graph is velocity, constant positive slope, constant positive velocity. And if there is a constant velocity, we know that the acceleration is 0. So those are what those graphs would look like. That's for the way up and for the way down and for the instant that it's at the top. That is what the graphs of motion would look like for that horizontal component of its motion.